I am particularly excited to introduce our speaker today, Jeff Horsburgh, who's an associate professor in civil and environmental engineering at Utah State University. And his research focuses on hydroinformatics, cyberinfrastructure, watershed hydrology, surface water quality, and human dimensions of water use. His work includes observation systems and sensor networks, data models, and development of cyber infrastructure supporting environmental observations, and using geographic information systems for data analysis and dissemination, and modeling techniques for surface water hydrology and water quality. So many of you know that in our most recent EQVI project, our EPSCoR award, that we were focusing on exactly these topics. And you may or may not know that the data products that were generated from that award, many of them have been uploaded into the software system that Jeff developed called Hydroshare. So this is super fun, looking forward to this. And also you may not know, but now will know that Jeff and Sean have worked together on some previous incarnations of some of these platforms. So super excited to hear this. So the title of Jeff's seminar today is Advancing Open and Reproducible Water Data Science by Integrating Data Analytics with an Online Data Repository. And we're going to hold questions to the end, but feel free to put them in the chat as we go. And Jeff, thank you very much for joining us. You look like you're right here in Hawaii, but I know you're not.
Well, yeah, let me go ahead and get my screen sharing going here. And I want to just thank you for that introduction. I appreciate it. And also thank you a lot for the opportunity to present to this seminar. I'm actually really glad to be here and to have the opportunity. And I also want to say, I'm going to talk to you about a lot of things today, and it's my name on the first slide here, but there's a huge team of collaborators that have worked on all of this stuff that I'm going to talk about today. So when Gwen said, I've worked on Hydroshare, I definitely did not develop that whole system by myself. There's a huge team of people that have worked with me. And my Zoom background, so when I first talked to Sean about doing one of these seminars, this is sort of what I was thinking about, right? Like a trip to Hawaii, I'll be on the beach. Well, about 2 weeks ago, it snowed like a foot in Logan. So we've already had like a foot of snow this year. So maybe next time, Sean, maybe next time. Okay, I want to just give you a really brief outline. I'm going to talk first about some challenges related to environmental data science. I doubt I'm going to tell you much that you don't already know in terms of challenges. I'm going to talk about some tools that we're developing and working on to address some of those challenges. And then I'm going to be really sneaky at the end and finish with some more challenges at the end. So just know it's coming. There's lots of challenges here. Okay, so I see a lot of surveys like this online, lots of articles. You know, people like to survey people and say, well, what do you do for your job? And what do you spend most of your time doing? And apparently, so I'm not a data scientist. I'm a civil engineer, but I do data science in part of my life. And so I would say this is pretty accurate when it comes to my work related to data science. Cleaning and organizing data, 60% of the time, collecting data sets, 19% of it. So most of the time is just like getting the data, getting it organized. This is nothing that you don't already know. And so hopefully for some of you, like that 5% other, like you're out doing things like surfing or doing something you actually enjoy. But if you look at what's the least enjoyable part of data science, like it's the same stuff, right? So cleaning and organizing, just getting the data, getting it into the formats that you need. So it still remains hard to get the data and get it in the format that you want and need so you can do the work that you really want to do. It's also true, particularly in domains like mine, engineering, that digital divides still exist pretty much everywhere we look, right? So, and here I'm talking about the gaps between those who have programming, data science, and computational skills and those who don't. Those digital divides are still quite wide. In a paper a couple years ago that we published in Environmental Modeling and Software, we talked about a few of these things. So there's a shortage of trained experts when it comes to data science, and that's because traditional engineering and science programs like mine in particular struggle to fit data science into their curriculum. Like we're so full of the engineering courses that we want our students to take that fitting another course where they're learning how to program, they're learning how to do data science, like it just doesn't fit in our undergraduate curriculum. And so when our students get here for graduate school, they're basically learning these programming and computational skills by themselves because they didn't learn it in their undergrad. And so in some ways, this kind of begs for changing our approach to education and workforce development, but it also encourages us to build collaborative teams because we know that we need to get those skill sets to work on interdisciplinary problems. But there's also these methodological gaps out there. We as engineers, we know there's good computational and data science methods out there, but we don't always know what the right methods are to apply to the applications in engineering. And I'm not going to talk about this second one as much today as the first one, but it does beg also for a need for developing new methods and tools and also figuring out how to apply the tools and methods that we have to the problems that we have in other disciplines. So I would like to plant the idea that cyber infrastructure can help bridge some of these gaps that we see. And so if we look at our toolbox, it might include lots of things like the programming languages that we learn, the coding environments that we have, the repositories that we use for our code, the different packages that we load into our programming environments, all of those sorts of things. And they really add to our ability to do data management, visualization, analysis. These all advance our capabilities, but sometimes they're not super approachable. And so building these tools in a way that makes them more accessible can help bridge some of these gaps that we know are out there. And we know that those tools are advancing, but one of the biggest problems is composability, right? And composability, when I'm referring to that here, I mean, how do we string together all of these tools that are in our toolbox to build something that's actually useful and helps us solve a problem? Now, a really common way of working in engineering, particularly that we've had in the past is we buy our students these big beefy computers. They sit on their desktop, this big tower. It's got lots of hard drives in it because they got lots of data. We buy them all the processors we can fit in that box and lots of RAM, and we load up all the software that we can get on that machine. But they're doing all of their work locally on that machine. They're doing their modeling, their geospatial analysis, and their data processing and visualization there. And the problem with that is it's sort of isolated, and it's really hard for them to share and reproduce the work that they've done because they've done it all on their own personal machine. And oftentimes we still run into scalability issues there because eventually their data get too big or their model doesn't run fast enough or all of these kinds of things. And so what we're seeing more and more of now is that all of us and our students are moving more to a cloud-based way of working where, they're working with a data repository like Hydroshare. They're getting their compute services from somewhere like Exceed. Maybe they're getting data from federal agencies that have data available via the cloud. They got to figure out where they're going to put all their stuff. So maybe they have some storage over in Amazon. And maybe they're using an online service like Jupyter Hub to do analysis and visualization. And this is a totally different paradigm. Which is great. And of course, you have to learn how to use all of these tools, but also you got to sort of figure out how to make all of these tools work together because you may be pulling data from online storage into your Jupyter environment, publishing your results to an online repository, and you're also combining with data from a federal agency, and you're putting that all into a model that you're running on a compute resource. And so you got to figure out how to make all of these connections work. And so this idea of composability means, how do I get all of these pieces across all of these systems to work so that I can do the job that I need to do? So if I summarize those challenges, there's good cyber infrastructure components out there. Like there's lots of great tools. We have the parts. So how do we connect them better to make it easier to do environmental data science? And that begs for some standardized interfaces between systems, things like application programming interfaces. And of course, if we've got APIs, it's a lot easier to use them. If we have some client code libraries for popular languages, that makes it easier to consume those. And also, if we're moving things around, it's really nice if there's standardized packaging and representation of data so we can move things around. And it would also be really, really nice if we could develop architectures that are transparent to users. And when I say that, I mean things like we all collaborate with systems like Google Docs. We don't care where the document is. We don't actually really care that much about how it works under the hood. We just care that we can work together in a Google Docs. So can the types of work that we're doing be that transparent? And of course, we need to continue supporting the changes in the way people work, because the students that I'm hiring now work in very different ways than I was taught to work when I was an undergrad or a graduate student. Okay, we also know that reproducibility is key, and this goes towards building trust in research, and that requires some transparency and reproducibility. And this is particularly a problem in computation, because you can't always reproduce computational research, because it requires that you reproduce the computational environment in which that research was done. And that can be really challenging for somebody who doesn't have the expertise needed to do that. So there's lots of questions surrounding this reproducibility problem that I'm going to talk about in my next set of slides. Now, there's some work coming out of some of my colleagues' research groups. So John Goodall's at the University of Virginia. He's got a bunch of students that are working on some work related to what it means to be reproducible. So we go through the steps of repeatability, runnability, reproducibility, and then of course replicability. And as you move from the bottom to the top of that triangle, of course, you're increasing the time and effort that it takes to actually get to the top of that triangle. And then they've proposed some ideas about what it means in a modeling context, where they're combining an online repository. In this paper that I've cited here, they're using Hydroshare, but they're also building model application programming interfaces, combining those with a computational environment and some containerization technologies to make this sort of circle between repository, APIs, and computational environment lead to a bit more reproducibility in the context of hydrologic modeling. So some of our broad goals, and when I say our, I mean the team of people working on Hydroshare and other related projects. One, we want to enable water data scientists and water scientists in general to more easily share and collaborate around data and analyses. Two, we want to provide data management, visualization, and analysis tools that advance their capabilities. And we'd love it if we could promote more consistent data workflows, data reuse, and reproducibility of scientific results through developing cyber infrastructure that supports this. Okay, so if I think about this at a very high, sort of 30,000 foot level, a collaborative investigator workflow might look something like this. So we want to easily create a digital instance of a data set or of a data science workflow, quickly share it with colleagues, perhaps privately at first, because it's not ready for prime time, it's not published, we're not ready to put it out there in the world yet, and probably we need some iteration first to make sure we got it right. We want to add some value through collaboration, annotation, iteration, all the things that we do when we work together. And then eventually we want to describe that with some metadata and share it publicly, or formally publish. And when I say formally publish, I mean publish with a capital P. So we put it in a repository, we get a digital object identifier and a citation so that people can actually go access it and see what we've done. And so a question that comes out of this is what's the role of data repositories and other repositories in this scientific workflow? So I'll talk a bit about that. And I'll do it in the context of Hydroshare, which is the repository that I've been working with most. There are other good repositories out there, so don't let me give you the idea that Hydroshare is the be all end all of scientific data repositories, but it's one that's used pretty extensively in Hydroshare or in hydrology now, which is awesome. Hydroshare is a web-based hydrologic information system and repository. It's operated by the Consortium of Universities for the Advancement of Hydrologic Science Incorporated. That's a mouthful, but they go by COASI for short. And it basically provides a place for creating and sharing data and models using a variety of file formats and flexible metadata. And you can think of it as a repository for sharing and publication that uses FAIR principles. Hopefully you've all heard the FAIR principles, but FAIR stands for findable, accessible, interoperable, and reusable. And in Hydroshare, we've defined this concept of a resource. It's the primary unit of digital content in Hydroshare. You can create resources, version resources, copy them, describe them with metadata. You can own them, share them, access them, discover them. And of course, you can formally publish resources when you're ready to do that. But you can think of a resource just as a container into which you can put digital content inside of Hydroshare. And that content could be a data set, it could be a model, it could be some other research product that you're creating. And the cool thing about Hydroshare resources is they have a formal, like a file or a content-based definition. So if you go to the landing page for a resource, you get this file content area and you see the actual file and folder structure of the resource. And so it's got this file content-based definition, but it also has a semantic definition that's based on the Open Archives Initiative's Object Reuse and Exchange standard, where basically you have a resource map document that's expressed in XML. It defines an aggregation of objects that are part of that resource, and then they're all associated together into this aggregation. And so you've got this sort of semantic definition of all of the files that are part of that resource, what the relationships are between those files, which metadata documents describe which data files, and all of that kind of stuff. So file-based definition, semantic definition in a machine readable way, which makes Hydroshare resources kind of unique. And another idea that I would like to sort of plant in your brains is that you could think of a Hydroshare resource as a data science enabler, because when you're creating reproducible data science workflows, you have to make some decisions about how you're going to organize the things that you're putting together. So if your eventual goal is to share that analysis, and I hope many of you are thinking, okay, I want my work to be reproducible. I want to share the analyses that I'm working on. I want people to be able to access my workflows. If your eventual goal is to share your analysis, then you've got to be able to get that, whatever code and data you're working with, into a repository. And you need some straightforward ways to organize that content, which might include input files, output files, code, all of those sorts of things together. And so Hydroshare resource is a potentially great organizing container. So you could think of it as a project directory that has an existing resource data model. It has a machine readable semantic representation of that structure. It's flexible. It has a file-based data model. So whatever files you can conceive of, you can put into Hydroshare. It has existing aggregation or content types that identify commonly used data. Now, since it's Hydroshare, those aggregation types are things like time series, geographic feature, geographic raster, multi-dimensional net CDF, a lot of the kinds of data that hydrologists use every day. So it's not going to cover everything that you might conceive of, but a lot of the sort of common things. And you can map the whole thing to Python for easy manipulation. And it's already handled by a repository, Hydroshare. So it's got a lot of things going for it. And I'll talk about how we've sort of advanced tools to kind of make this happen. Okay, so if we take our 30,000 foot level view of the workflow and start thinking about a little more specifically, how do we connect visualization and analysis with an online repository like Hydroshare? So let's say a researcher like myself wants to pull data from the United States Geological Survey into a local Python environment for doing some visualization and analysis with other data sources. And so they need a tool to get the data. And once they've got that data in their local Python environment, maybe they're programming some visualization and analysis, they're writing some scripts in Python, they want to share both the data and the research results. And so they might use another tool to actually push their data and scripts to a Hydroshare resource. They upload their code, their data, they add metadata, and then eventually they share that analysis in Hydroshare with a digital object identifier in a way that people can actually access and go get it. And then what that means once it's in Hydroshare is that somebody could pull that resource down into their local Python environment. They could re-execute the code. They can examine the results, reproduce, and they can potentially extend that workflow if that's what they're interested in doing. And there's also no reason why, instead of using their local Python environment, they couldn't pull that same package down into, say, a Jupyter Hub environment. Hydroshare has a linked Jupyter Hub environment for doing the sorts of things that I'm going to talk about here in a few minutes. You could pull that same package down, run the code, generate the same results, get the same visualizations, all of that kind of stuff. So this is getting a little bit more specific. Hydroshare is kind of in the center here, mediating across the people who are producing content and the people who are potentially consuming that content to reproduce the results or just sort of visualize and see them. There's some tools that we need to make that workflow work. So obviously we've got the data repositories that we're working with. We're working with Hydroshare. Hydroshare has a REST API. We're working with the United States Geological Survey. Their National Water Information System also has a REST API. So we're not doing a lot of work there. Those tools already exist. But we've built some additional tools for accessing and interacting with those repositories. And these are Python packages. There's two of them that I'm going to talk about. I'll briefly talk about the USGS data retrieval Python package. I'll spend more time talking about the Hydroshare client package because we've spent more time on that package. But once I've used those packages, I need to get the information from those two repositories into a structure, either in my local Python environment or some other Python environment, into a structure that I can actually manipulate. And I don't want to spend a huge amount of time like reading files, parsing files, organizing things into performant data structures, because what I really want to do is use tools like NumPy or scikit-learn or matplotlib or pandas, whatever the tools in Python are that I'm doing my analysis with. I want to be able to act on whatever's in this Python object data model directly. Okay, so I'll talk about each one of these tools. So as I said, we've built two new Python packages. Our goal here was to enable simpler interactions with data repositories in your Python environments. So we're working to advance data access, collaboration, and data archival capabilities of Hydroshare. And this goes back to that sort of original slide that I showed you, where data scientists are spending all of their time organizing data, getting data, cleaning it up, and getting it into formats that they can use. These packages are designed to really streamline that effort. Let's get the data directly from the repository into a format that we can use by calling, one or two function calls in a Python library rather than dealing with a bunch of files and figuring out how to parse them and load them into structures. Okay, so the Hydroshare Python client library is called HSClient. There's a GitHub repository for that. It's also in PyPy. So if you want to pip install it, you can pip install it from PyPy. It's got a bunch of functions for creating and editing resources in Hydroshares. You can interact with resources in an interactive, object-oriented way. And our objective with the HSClient package was to essentially enable all of the things that you can do through the web user interface of Hydroshare using this Python client package in your code. And in a way that makes it a lot easier for people who are working sort of with data science workflows, because they're a bit more power users. They want to get the browser out of the way and just get data moving back and forth into their environment in the repository. So again, we're working to reduce the time required to get data for analysis and then save results back to that repository. If you're interested in checking out HSClient, there's a set of Jupyter notebooks shared in a Hydroshare resource that basically show you how to use the HSClient package. And then of course, you can go check it out in the GitHub repository. You can install it from PyPy if you want to. Now, if we look at the combination of the HSClient Python client and the Python object data model, this is the structure that we're using in your local Python environment to store whatever we're getting back from the repository. The structure of a Hydroshare resource is specified in an OAI ORE, RDF XML, what's called a resource map document. And it's RDF XML, and if you have any experience with RDF XML, like, it's really useful for expressing information, but it's really not human friendly. So you don't really want to be like opening these things up and dealing with them. You want to use code to deal with this. So HSClient translates that structure to a Python object representation, reads the RDF XML into a Python structure, reads all of the metadata, gives you basically an object-oriented view of that metadata that you can manipulate in your Python environment, whether it's your local environment or a Jupyter environment. And then if you manipulate that and change it, you can call some simple functions to save that structure and then send it back to the repository. And that allows you to modify the RDF XML representation of the metadata outside of the repository, and then send those files back to the repository to be ingested. So we wanted this to be a relatively flexible water data science object model with the idea that you pull data out of the repository or build data locally within this object model and then send it to the repository. And we wanted to enable this to map common water-related data types. Think of the Hydroshare content types that I mentioned: time series, rasters, geographic features, multi-dimensional netCDF. Wouldn't it be nice if those data types exist in a Hydroshare resource and I can call one function call to say, give me that time series as a pandas data frame. And then I don't have to read a file, I don't have to parse a file, I don't have to load it into a panda data frame. I can just call one line of code that gives me that known content type back in an object that I can then manipulate using whatever Python tools that I'm using. So it's focused on loading and staging data for visualization and analysis with whatever tools you're already using in Python. We implemented that object data model using a tool called Pydantic. It exists as a set of classes that are defined using Pydantic models. Those models define the metadata structure and validation for Hydroshare resources and the data within them. So a class contains what are the required and optional metadata elements, what are their data types, what are their, sometimes there's value validation in these Pydantic models. And what that enables is all Hydroshare resource metadata to be represented in Python objects based on those models so that you can reset the title and the abstract and the keywords and all that kind of stuff using object-oriented function calls in Python. And then when you're done, you can easily write your edits back to Hydroshare because we're now basically ripping the guts out of Hydroshare, where we used to be representing all of this metadata using a Django database under our Django application. And now we're using these Pydantic models to basically use a file-based metadata structure in Hydroshare, which we had already, but we were using the Django database, which kind of led to an occasional hiccup with inconsistencies between the database and the files, which was pesky and hard to deal with. So we're also using this in the back end of Hydroshare. As I said, there's a set of Jupyter notebooks that show you basic resource operations, file operations, moving data and files into and out of Hydroshare, metadata operations. And just to give you a little flavor for this, like there's functions for authentication with Hydroshare. So in code, you can authenticate, you can create resources. Once you've created a resource, you can call a function on the metadata to set the title, the abstract, the subject keywords. Once you've set those, you can then call a function to save it. If you want to delete a resource, you can take that resource that you've got and you can just delete it. You can download a full resource, tell it where you want to put it on your local disk, or you can download individual files from resources and put those on your machine. You can upload individual files to a resource, and if you want to delete files, you can delete. So basically, the HSClient package has all of these create, read, update, and delete operations for Hydroshare resources. So you can manipulate Hydroshare resources all in code. Those content type aggregations can be manipulated using functions in HSClient as well. The pattern is that you load the data files to the resource, you get the type of aggregation that you want, and then you basically apply that aggregation to the files in Hydroshare. And then once you've applied an aggregation, those aggregation types can have their own metadata. So you can have a title, subject keywords, all of that kind of stuff for aggregations. So there's multiple levels of granularity of metadata in Hydroshare that you can apply. Now, we also wanted to complete the pattern because it's all great if you can move files in and out. It's great if you can manipulate the metadata, and that's really useful. But what about the actual data files themselves? We want to provide some convenience functions that save you time for actually loading data into a performant data structure that you can actually do something with. So, for example, if I've got a set of time series of data in a Hydroshare resource, those time series might have been collected a streamflow gauge or a water quality monitoring site or something like that. And I want to load those time series into a performant data structure like a pandas data frame. Then I could basically say, give me this time series and aggregation.as data frame. I get it back as a data frame. And now I've got a data frame object that has all the time series values indexed by date time, and off you go to do subsetting, aggregation, plotting, or whatever else it is that you want to do analysis-wise with that time series object. Okay, so that's also where we're currently working with HSClient. We've got this done for time series, but we're working on geographic feature, geographic raster, and then the multi-dimensional NetCDF files we're also working on. We've mapped those to performant data structures, and now we're actually working on the functions to actually load them using that simple pattern that I've just showed you. All right, so that's HSClient. I also mentioned that we've developed a USGS data retrieval Python package, and when I say that, that's a bit of an overstatement of what we actually did, because when we got the funding to do this work, we weren't aware that there was actually a semi-complete implementation of a USGS data retrieval package already in GitHub that was written by a guy named Timothy Hodson at USGS, which turned out to be really great for us because we didn't have to do as much work as we thought we were going to have to do. This is essentially a Python mirror of the R data retrieval tool. So if you're familiar with the R tool, it's very similar to that. It currently has most of the same functions, very similar results. So instead of a data frame in R, you get back a pandas data frame in Python. So the patterns are very similar depending on whether you're using R or Python. Again, there's a set of example Jupyter notebooks if you want to learn how to use the functions in the USGS data retrieval Python package. And it's also available in PyPy if you want to pip install it into your Python environment. Okay, so just to give you a flavor here, if you want to get, say, daily streamflow data for any USGS streamflow gauge in the country, you create a site identifier, you tell it which parameter code, so 00060 happens to be streamflow from USGS, give it a start date and an end date, and you call one function, get underscore DV, pass it the site ID, the parameter code, the start date and the end date, and what you get back is a pandas data frame with the time series of daily streamflow values for that streamflow gauge, for any streamflow gauge that exists in the National Water Information System. And so that's the daily streamflow values, but there's functions available for daily values, the 15-minute unit values. So if there's a real-time streamflow gauge and you need those, you can go grab those. Groundwater water levels. There's functions for retrieving information about monitoring sites. You can get the actual discharge measurements and rating curves that they use to generate their real-time streamflow data. You can get statistics and also some water quality data, which we've implemented functions for, but haven't really tested those. So buyer beware, the water quality functions are not fully tested yet. But mostly this package is working. It's been around for a while and we've enhanced it, but a lot of the work that you're going to see there was actually done by Timothy Hodson at USGS. Okay, so I've talked about some of the tools. Now, if we go back to our workflow, got Hydroshare here in the middle, and we can think about a local Python environment or a Hydroshare Jupyter Hub Python environment. And so we have this question like, how can we re-execute the things that we share? If we take our analyses, we use a resource in Hydroshare, we organize things in there, we upload them, we share them so somebody else can get them. How do we actually re-execute those things, or how does somebody else re-execute those things so that they can get the same result that I got and that's shown in figure 7 in my paper that I just published? So one option, of course, is we tell them, well, you need to create a local Python environment that looks just like my local Python environment, except my local Python environment might not be a very pretty picture, right? So this comic from XKCD, my Python environment has become so degraded that my laptop has been declared a Superfund site. I'm sure none of you know anything about what this comic is referring to here. So you have to set up your local Python environment. You have to get the Python version right. You got to install all the right versions of all the packages, which may not be backwards compatible. And then you cross your fingers and hope that it's going to run when you get all that set up. That may or may not happen, right? I'm seeing some smiles so I'm sure this is something that people have some experience with here. So now virtual environments can help. So on your machine, you set up a clean virtual environment, you install stuff, but that can still be really challenging, right? So how do we move to something a little bit better than The Hydroshare team and Kuwazi are working towards more collaborative and interactive computing for water data science. They're putting together and have supported for quite a long time a Hydroshare linked Jupyter Hub. They're running that in the Google Cloud, and it currently supports unlimited users, but Kuwazi's paying for that. And so I think there probably are some practical limits to that. But it is capable of creating classroom or workshop specific instances. So if you're running, say, a hydrology course, and you want all of your students to be running a Jupyter notebook, it is capable of doing that scale of computing. And it is completely customizable and uses the latest Jupyter Hub software. But I'll talk about some more of the limitations here in a couple minutes. There's another Hydroshare linked Jupyter Hub environment. It's called CyberGIS Jupyter for Water. It has some additional compute resources. It's actually hooked up on the back end to an Exceed allocation. So you can actually run some more intensive computational stuff via Jupyter notebooks in CyberGIS Jupyter for Water. Kuwazi is also running an instance of MATLAB online, and it's limited to 50 concurrent users, but you can live script using M files, and there's like 20 plus toolboxes that are in there. I don't know a ton about MATLAB because I'm not a MATLAB person, but it's also linked to Hydroshare. And I will talk about Binder and my Binder right at the very end. So what does this mean? Like how does this linkage work? I said it's linked to Hydroshare. So let's say I create a resource in Hydroshare and I put my data files in the content of this Hydroshare resource. And then I were to put a Jupyter notebook in the same directory of this Hydroshare resource. And maybe that Jupyter notebook acts on that data file that I put in the same resource. I can go up to the top of that resource and I can click on the Open With button and I get some options. I can open it with MATLAB Online or CyberGIS Jupyter for Water. But if I choose Kuwazi Jupyter Hub, then it basically launches and spawns a Jupyter Hub environment, and it goes and gets the data from Hydroshare that is in that resource that I just launched from, moves all of that data over into Jupyter Hub, and then I can launch that Jupyter notebook and run it in the Hydroshare linked Jupyter environment. So this is a way for us to enable people to share data in Hydroshare, but also the code that they use to analyze those data, maybe it's for a paper or some other analysis, together in the same repository and in a way that users can actually go and they can launch that into a computational environment and then run through that Jupyter notebook cell by cell and actually look at the results. So Hydroshare becomes something of a gateway to high performance computing because like the Kuwazi Hydroshare Jupyter Hub for Water actually has capabilities to do high performance computing behind the scenes, which is pretty cool. Okay, so how does this Hydroshare compute workflow work? So you've got your Hydroshare resource, you click on that Open With button, it requests an instance of the Hydroshare Jupyter Hub environment. It sets up your own Jupyter Hub environment for you as a Hydroshare user. That requires you to authenticate with Hydroshare. And then once you've done that, that Jupyter Hub environment goes to Hydroshare, requests the data from the Hydroshare resource, which gets sent back to that Jupyter environment as a zipped file. It gets unzipped, put into your working directory, and then if there's Jupyter notebooks inside your working directory, you can actually launch those and operate on data that are also in that same directory. So this is all work that's being done by Tony Castronova, who's at Kuwazi, who's really running all of the Kuwazi linked Jupyter Hub environment stuff. Okay, so another really cool thing that they have built, because we realize, all right, we've got these linked environments now, but it starts to get a little bit tedious when you launch everything over into the Jupyter Hub environment. You do some cool work there to modify your Jupyter notebook, you add code to your Jupyter notebook, you know, you've sorted everything out and you're like, okay, wait, now I want to share this result back to Hydroshare. It's actually a little bit tedious to move those edits that you've made to that Jupyter notebook back to Hydroshare. So Tony and a guy named Austin Rainey, along with a group of students from the Olin College of Engineering, developed an application that lives inside this Jupyter environment. That's called the Hydroshare Jupyter Sync app. So once you're in that Jupyter environment, you can launch that Jupyter Sync app, and it basically gives you a window that shows you all of the resources that you have in Hydroshare. You can select one of those resources, and then it shows you the list of files inside of that resource. And you can click on the button to download files to your local Jupyter, your Jupyter environment. So you've got your files in your Jupyter environment. It shows you your files in your Hydroshare resource. And then of course, you want to open one of those files. So here I've got my Jupyter notebook open. Maybe I go to the end of my code, I make some changes to the code, I add a new line of code, I print something, I do whatever. And so I've modified my notebook, and now that's shared in, or that's saved in my Jupyter environment, but it doesn't exist in Hydroshare. So when I go back to the Hydroshare Sync app, it shows me, oh yeah, the icon has changed, this notebook file is out of sync with Hydroshare, and then I can do one of two things. I can either say, yeah, I want to keep those edits, so let's upload those files to Hydroshare, or maybe I was just playing around and I don't want to keep those changes, so I'm going to download files from Hydroshare and replace them in my Jupyter environment. So this is working a lot like, many of you may have toyed around with like the GitHub client for Windows or Mac for moving files back and forth. Most of you probably work with GitHub from the command line, but those desktop clients are a lot more approachable for mere mortals who don't spend their lives working at the command line and want to see a visual representation of what's here and what's there, what's different, and which ones can I move back and forth. Right, so if you're working directly in the Jupyter environment and you want to work from the command line, you surely can use HSClient and you can move those files back and forth because Jupyter, the HSClient library is actually used by the Jupyter Sync app. It's like the same thing. It's just a visual interface for the same things that you could do at the command line. Now, I said I would talk about some of the limitations of Hydroshare's linked Jupyter environment. It's still better because I don't have to set up the environment, and better yet, the people who might want to rerun my code don't have to set up the environment. And there's some nice tools like Jupyter Sync for interacting with Hydroshare, but I still need an environment, right? I still have to have that environment to execute it. And there are some potential limitations like software dependencies. Now, Tony's doing a great job of creating some environments, and you can see his environments with the Jupyter Hub server options he's got here. He's got a Python 3.8 environment that's got a lot of scientific libraries in it. He's got an R environment, so if you want to do your notebooks in R, you can do that. There's some modeling environments where he set everything up to do some hydrologic modeling. That's all great. But what if that environment doesn't actually include the libraries that you need for the Jupyter notebook that you've developed? It is customizable, so Tony's left it open so that you can put an install line at the top of your Jupyter notebook and you can install libraries into your environment. But what if you have legacy code? Like what if you have Python 2.7 code? Happens still. There's no Python 2.7 environment here to run Python 2.7. And it also may be true that you have complicated and large input or output, and there may be some constraints of this computational environment, like the files are just too big, it's difficult to move them back and forth. And so there are still some limitations here, even though this is moving definitely in the right direction. Now, so one of those problems is, well, what if Tony's Python environment doesn't match the Python environment that I used to develop my notebook? Kawazi's playing around with Binder, which is a technology that allows you, they started out with GitHub repos where you would define an environment in a GitHub repository. You would point Binder at that GitHub repository, and then Binder would spin up an environment that matches your specifications, and then you could run whatever code you want to run inside that environment. So what Tony's done is he's done the work to actually add Hydroshare, a Hydroshare resource, as one of the places that you can point Binder at to get that definition of an environment, and then you can launch that Binder environment to run whatever code that you've got. Now, again, Binder is not going to give you all the computational resources in the world, but if you've got relatively simple, straightforward stuff, this could be a really cool resource because it spins up the Python environment that you specifically want. Okay, and you can actually start with one of Hydroshare's base images if you want to. All right, I've been talking for a long time, and I promised that I would pull a fast one and come full circle back to some challenges to think about at the end of my talk here. So What does it mean for computational science to be reproducible? I hope that's a question that you're all thinking about, that crosses your mind all the time. And I hope you're thinking about, when you're doing your scientific work, I hope you're thinking about, how do I share this in a repository? How do I get it out to people in a way that they could actually redo, reuse, or build on the work that I've already done? And so, of course, that begs some questions about how to best link repositories, how to share research products to computational and execution environments so people can redo what you've done, how to share that access to data and computation, and how to promote more consistent data workflows and data reuse, because it might actually be nice if we were doing similar things in similar ways, if we can. And also how to provide the right computational environment. So here I'm thinking of like the Tony Castronovas of the world that are running Jupyter Hub environments and trying to figure out, how do I support a broad group of hydrologists and water data scientists in providing computational environments that are actually going to work for them to do the work that they need to do, so that they don't have to set up their own Jupyter Hub environment. And then also how to overcome platform and library dependencies that sort of plague us day after day when we're trying to, get our work and our students, working together, and somebody's on Windows and somebody's on Mac, and the libraries are not exactly the same, and they're not getting the same answer, all of those sorts of things. So how do we overcome? And I hope some of the tools that I've presented today give you some ideas about how we're thinking about some of those problems and how we're going about solving some of those in the hydrology and water science domain. So with that, I will say thank you again for the opportunity to fill your mind with some of these ideas, and I'm happy to take whatever questions that you may have.
All right, thank you, Jeff. That was outstanding. It's especially just so pertinent for all of our graduate students that are here, part of our data science fellows. We've been talking about a lot of these different applications, so this is just an excellent real world example. I think Sean has a couple of questions for you.
So Jeff, so the OAI metadata stuff that you referenced, and the mappings to Python objects and models, that's pretty awesome stuff. Because yeah, that XML stuff is not fun to work with. Do you have a standalone API or anything for how you guys you go back and forth with that, or is it just embedded like as a part of the Django app that is Hydroshare?
So Scott Black, who is the main backend Hydroshare developer that actually developed all this work, he's got a repository that's called HS Models, and it includes all of those pydantic models that are essentially pydantic representations of the exact same metadata that are stored in RDF XML. And he created code it's obscurely called bag ingestion, because we use this specification called Bagit, which is basically just a zip serialization packaging mechanism for putting together all of the content files for a Hydroshare resource, plus all of the OAI, ORE resource map and resource metadata documents into one zip file. And he called all of that bag ingestion because basically it allows him to take the OAI, ORE representations of the resource map and the metadata and ingest them into the pydantic models. And so the combination of HS models and the code that he's written around that, I think would basically satisfy what you're asking. Whether we don't have an external facing API that actually like sort of shows you that mapping, but I think you could probably learn a lot from what Scott's done to move back and forth between the OAI, ORE representation of metadata and the pydantic models that we've defined.
Okay, yeah, no, that sounds pretty interesting, and I think probably pretty useful and applicable for a lot of applications that are looking for fair support and having to mess with RDF.
Yeah, RDF XML, it's not pretty, and it's actually kind of hard to work with. But OAI ORE is a standard. It gives you something to hang your hat on, right? And with Hydroshare, we're leaning much further towards strictly file-based everything, because we kept having issues where our Django database underlying Hydroshare was getting out of sync with the files that were actually stored on disk. And we had to run management commands in Django to sort of fix things and all that kind of stuff. And it just, like, all of this, the Pydantic models and going file-based everything just solves all of those problems that we were having. Plus, the added benefit is we get all of the HSClient and all of our REST API stuff becomes much more simple and useful, which is great.
Can't beat that.
Yeah.
Can't beat simple. Okay, I have a follow-up question about the Jupyter Sync stuff. Is that like a widget or like something you can install into a separate like Jupyter instance, or is it like some crazy custom stuff that had to happen to the quasi Jupyter Hub?
So my understanding of that is that it's currently written as a Jupyter Labs plugin.
Okay.
But I'd have to put you in touch with Tony and Austin, because they were trying to make it as generic as they possibly could, to the point where we've even been considering not just using it within Coasity's Jupyter environment, but also people using it potentially in their own local Jupyter environment, because you can, of course, run Jupyter on your own machine. And they wanted to enable that. But I've also been thinking, well, what if I'm not using Jupyter at all? What if I'm just programming in Python or doing other stuff and I want to sync files back and forth to Hydroshare? We've debated a lot, like how far down the Git road we want to go in terms of, like, the conflicts and conflict resolution and all of that kind of stuff. And we're still a little bit undecided about that. But that the sync client does make it a lot easier to work back and forth. You don't have to write lines of code to move files back and forth. You can just click a button, which is great.
Yeah, no, if it's a plugin, then that's awesome, because I mean, we have Jupyter environments on our HPC system, and if someone just installed this plugin, then they could access Hydroshare repositories and move back and forth just from our stuff and be able to leverage our HPC resources. So
yeah, I know Tony would actually be really stoked if you contacted him about that. So I would say definitely get in touch with him.
Okay. All right. Thanks, Jeff.
Great, thanks. I think, so we have a question from Yufen. Yufen, you'd like to go ahead and ask your question? Where are you? Maybe she's not here. All right, I will read the question. The question is, thank you for the great talk. I want to double check, does it mean that for having a reproducible project on Hydroshare plus Coasi Jupyter Hub, does one need to work on the Hydroshare and Jupyter Hub from the beginning instead of uploading the work later? And secondly, is there a limitation on how many people can work on Coasi Jupyter Hub at the same time?
Yeah, those are both great questions. So the answer to the first question is no. You can totally write your Jupyter notebooks in your own local environment if you want to do it that way, or you can use some other Jupyter Hub environment if you want. You can download the Jupyter notebook, you can upload it to Hydroshare, and then it should, I'm going to say should, right? It should run no problem in Hydroshare's linked Jupyter Hub environment, because Tony's using all the latest Jupyter Hub technologies there. So the answer to the first question is no. I think there is a practical limit to the number of people that can simultaneously use Hydroshare's Jupyter Hub environment, although they're running it in the Google Cloud. And so what that means is that each person basically gets their own Jupyter environment, and it's spawning those environments as you request them. And it also means that the more people that requests environment and the more people who use them, the more Coasi pays. But that's generally, I think, a good problem for Coasi to have. I mean, they may eventually run out of money, but it also gives them a really great reason to go back to NSF and say, hey, we're supporting this really great service for the community, And oh, by the way, it's getting used a lot. And oh, by the way, we're out of money. And wouldn't you like to keep supporting this because we're providing this really great service for the community? And NSF may say, yeah, that's great. Or they may say, no, you need to find another way to pay for that. And Kuwazi has to deal with that. But at least Kuwazi as a community serving organization can say, we're doing our work to support the community. And so I would say, if you're teaching a class and you want 30 students to access the the Kuwazi Jupyter environment, no problem. If you're teaching a class and there are 500 people online at the same time, probably we're going to run into some scalability issues there. So again, I would say if you really want to use this for something that scales, talk to Tony and he can tell you where the practical limits are.
Great, thank you. Jeff, I have a question. This is primarily for our students. You mentioned earlier in your talk that you spend a lot of time cleaning your data and that's not the most fun thing to do. Do you have advice for our graduate students about how to avoid having to clean up their data?
Well, so that's a really hard, so I will answer that question in a number of different ways. So number one, I think it's important to be using data from reputable sources. Like if I am pulling data from the USGS, for example, I'm a hydrologist, I need streamflow data, I go get it from a reputable organization like the USGS, chances are it's going to be in a standard format. I'm not going to have to do a ton of work to format that data. But the USGS may not have data where you need data to do the analysis that you need to do. And so you may have to go to a state or local organization and pin them down for the data that they have. And then they email you a spreadsheet that has one column with no column header and another column with numbers in it. And one's like, the Julian day since whatever. And then the other column is some numeric hexadecimal representation of the streamflow, and then you got to make phone calls, right? So in some respects, there's nothing you can do if you need the data and you're getting it from a place where it actually needs to be manipulated and cleaned to the point that that you need to do that. But I would recommend in the process of cleaning that data and preparing it for whatever workflow that you're doing, first of all, don't mess with the raw data, right? You got the data in a format that you got it. Don't mess with it because you never know when you're going to make a wrong step and you need to go back. Mm-hmm. But second of all, if you can, script everything that you're doing, because then whatever you've done to that raw data is reproducible, right? To get from point A to point Z, I had to do 26 steps, and here they are in a script, and you can see exactly what I did. And that's reproducible. If you do a whole bunch of stuff in Excel and then you save that Excel spreadsheet as a CSV file, nobody's going to be able to reproduce that, right?
Awesome.
That may not be the best answer to your question, but that's the one I'm going to go with right now.
That's great. How about advice for students that are actually collecting their own data?
My first advice would be think it through to the end. How are you going to use these data? And also, how can you add value to the data that you're collecting by anticipating how other people might be using the data? Think about your close colleagues, think about people within your own institution, and then think about people in the world at large who may be reviewing papers that you're submitting, who may want to reproduce the work that you're doing. It takes a pretty strong commitment up front. I'm finding with my own graduate students, it takes a pretty strong commitment up front to put in the time and effort to make your data collection and your analyses reproducible. Mm-hmm. But if you do that, the dividends pay off in the end in a lot of ways.
Great, thank you for that. I think that's one of the messages we're trying to really get out there to folks, that the better you manage your data on when you're collecting it, the less trouble you'll have later in cleaning it up. So awesome answer, thank you. And I know that many of the folks, many of our students here are downloading data from different resources, USGS and others. So that's really great advice for them to help think about, just how are they going to trust those results depending on those different data sources. So Really awesome. All right. Any one last question for Jeff before we take off? Anybody have any other questions? Looking around. Everybody got their hand up. Okay. All right. Not seeing any other questions. Jeff, I want to thank you. And I would really, we were really serious about having you come out here and visit us, I think. It would be super fun. We have a lot of folks that work in environmental science. It would be a lot of fun to have you come and give a workshop on Hydroshare and really help folks figure out exactly how we do this stuff hands-on. That's one of the things we like to do in the Data Science Institute. So consider this an open invitation. We'll get you back
Awesome.
here. And then you can, take that picture home with you and tell people you were actually there.
Sounds great. Thank you. And thanks again for the opportunity to present. It was great.
Oh, you're welcome. Okay, round of applause. Thank you so much, Jeff.
Thanks, Jeff.